Hello Science fam, this is going to be our worksheet number 2, practice with Lewis dot diagrams. Hopefully you're starting to get a little good feel for what a Lewis dot diagram is. But remember, everybody wants 8 valence electrons except for hydrogen. Hydrogen's happy with 2. And you could only use the amount of valence electrons that you start with between all the different elements. So let's name this. This is 1 carbon, so we're going to call it carbon. And there's 1 oxygen, so we'll call it monoxide. Covalent compounds, remember, use the prefixes. All right, so I have 1 carbon, 1 oxygen. If I look on the periodic table, carbon's in group 14, so it has 4 valence electrons. And oxygen's in group 16, it has 6 valence electrons. So that means we have 10 total electrons we want to use so that when they bond together, everybody's touching 8 electrons, all right? There's only 2 of them, so there's no one in the middle. But let's start by giving them each a single bond. We'll also give them each their own lone pairs of electrons. So when we do that, now everybody's happy with 8. Count around how many electrons are around carbon. There's 8. There's 8 electrons around oxygen. So that's a total of 2, 4, 6, 8, 10, 12, 14. Okay, so again, we run into the problem where we're using too many electrons, all right? So if we have 14 electrons and we did a double bond instead of a single bond, that would use 2 less electrons because we're sharing more. So that would take us from 14 to 12. So if we did a triple bond, that should take us from 14 to 12 to 10. Well, let's try it though and see for sure. So if we have a carbon and an oxygen, and we do a triple bond, that's 6 electrons in between. And since they're each touching 6, they'd each have 2 lone pairs of electrons on the outside. All right? So again, if we count up, that's 2, 4, 6, 8. 10 electrons we use total. 6 and 2 is 8 for carbon, and 6 and 2 is 8 for oxygen. So everybody's happy with 8 electrons, and we only use 10 electrons total. So that means that triple bond between carbon and oxygen is what works best to get your Lewis dot diagram. And there you go. If we move on to the next one here, we have 1 sulfur. So we're going to name that sulfur. And 3 oxygens. Tri is the prefix for 3. So we're going to call it trioxide. There you go. Now if we start doing our math, each oxygen we know, since it's in group 16, has 6 valence electrons. And we know sulfur, being in group 16 as well, also has 6 valence electrons. So we add up all those 6s, we end up with 24 electrons. So we have to somehow figure out how to get all of these connected to each other with only using 24 electrons so that everyone's still touching 8. Now, someone might say, wait, I thought sulfur was an exception. Doesn't it hold 10? Good point. Only if we let you know that it's an exception. Normally, though, sulfur just wants to hold 8, just like everybody else. Every once in a while, that doesn't happen. But always assume that sulfur just wants 8 unless you're told otherwise. All right, sulfur's the oddball by itself, so I'm going to put sulfur in the middle. I'm then going to surround sulfur with oxygens, and I'm going to give each sulfur-oxygen bond a single bond. Now, there's only 6 around sulfur right now, so I'm going to give it a lone pair. Each oxygen only has 2, so I'm going to give each of them 3 lone pairs. And when I add all that up, everybody's happy with 8, but when I count these electrons, I end up with 26 instead of 24. So that means I have a few too many. Now, what do we do when we have too many electrons? We need to do a double bond somewhere, or triple bond. So the only place that I can take electrons away from is really from this sulfur. If I take away from that and I put those electrons somewhere else to make a double bond like that, if I do that, that's great. Now sulfur's still touching 8, but now this oxygen over here is touching too many. So I need to erase these 2. What did that do? That ended up making a double bond on one of the oxygens, And now instead of 26, by making a double bond, I'm using 24. But look, sulfur's still touching 8. This oxygen's still touching 8. This oxygen's still touching 8. And this oxygen is still touching 8. So when we write that out, one of the oxygens has a double bond and the other ones have single bonds. Now, does it matter which one has the double bond? No. We could have wrote it so that the bottom one had a single bond or the side one had a single bond. I just chose this one at random, so that doesn't matter. But that is okay. They don't have to all have a double bond. So in this case, for sulfur trioxide, only one of them has the double bond. If we look at the next one, number 3 here, H2O2, you have 2 hydrogens. So we're going to call that dihydrogen. And 2 oxygen is dioxide. We also call this, besides dihydrogen dioxide, its regular name is hydrogen peroxide, which you can clean cuts out with. All right. Sulfur trioxide, by the way, number 2, is a smelly kind of rotten egg smell, given off in factories sometimes. And then carbon monoxide is definitely a bad gas. It's scentless. It can kill us. Sometimes given off in old furnaces when they're not going well and working well. So we always have carbon monoxide detectors in our house. All right. So now that we got a little bit more room, let's work this out. We've got 2 hydrogens and 2 oxygens. Each hydrogen's in group 1, so they have 1 valence electron. Each oxygen's in group 16, so they have a total of 6 each. That gives us a total of 14 valence electrons we have to work with. All right, remember hydrogens are always on the ends because they can only hold 2 electrons and be stable. So it's not like they can create more than 1 bond. They always create a single bond. So I'm going to put my oxygens in the middle and my hydrogens on the outside. Again, I'm going to try to make it look as symmetrical as possible. So that's why I put a hydrogen on each side instead of 2 hydrogens on 1 oxygen. All right. Well, if I start putting in my electrons, I know my hydrogens are already happy with single bonds because they only hold 2. So I'm just going to fill in the rest here so that each oxygen is touching 8 electrons. And when I do that, I count up 2, 4, 6, 8, 10, 12, 14. For the first time in a while, it seems, it actually worked out well. Everything is single bonded, and I used 14 electrons to give everybody either 2 electrons for hydrogen or 8 electrons for oxygen. So everyone seems pretty happy there. So if I wanted to write that with the dashes instead of the dots, you can write it either way. I would write it out, my Lewis dot diagram, like that for the single bonds. Either one of these is totally acceptable for an answer, though. All right, but that one was nice, pretty straightforward. Let's look at number 4. Number 4 is carbon dioxide, right? It's 1 carbon and 2 oxygens, which is dioxide. We exhale carbon dioxide. It's super important in photosynthesis for plants to eventually create food, and then they turn that carbon dioxide into oxygen. CO2. Each carbon has 4 valence electrons. It's in group 14. Each oxygen has 6, which gives us a total of 16 electrons to work with here. All right, carbon's the oddball, so I'm going to put carbon in the middle, oxygen's on the outside. I want to give everybody 8 to start so that they are stable, and then from there we'll see if we use too many electrons. If we did, that's fine. Then we just have to start making double bonds or triple bonds, okay? So we've got a single bond from each carbon to oxygen, so I'm going to need 2 lone pairs of electrons on carbon. I'm going to need 3 lone pairs of electrons on oxygen. And when I add all that up, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, I use 20 electrons. 20 electrons is way too much, right? We need to use 16. So if we did a double bond, that would take away 2 electrons total, and I'd be at 18. So if I did another double bond or another triple bond, that would get me to 16 electrons. So I think that's what I'm going to try next. All right, I'm going to give each oxygen-carbon bond a double bond. All right, so I'm going to erase a little bit here. And when I do that, remember, because I want everybody to have only 8 touching, I'm going to do a double bond between this oxygen, so only 2 lone pairs should be on oxygen in order to get 8. I'm going to do a double bond on this carbon-oxygen bond. Oops, I need to get rid of that one extra set of electrons on carbon because we can only have 8. And then you can only have 2 lone pairs on oxygen as well. So let's see here. Did I use 8 for each element? Yeah, there's 8 for this oxygen, 8 for this carbon, and 8 for this oxygen. So if I look at it double bond wise, let me make sure that I used only 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. And I did. So perfect. My Lewis dot diagram worked out. It looks like carbon dioxide has a double bond between both oxygens. Now you might be saying, well, could I have done a triple bond and a single bond and still gotten 16 electrons? And the answer is yes, you could have. And in theory, carbon dioxide probably bounces back and forth between 2 double bonds and a triple and a single. But since we try to make things symmetrical, try to get in the habit of, if you can make a double bond with another one instead of a triple bond with one, try to spread out those bonds. That just seems to be a good rule of thumb. All right? Hopefully we're doing good here. That's part 1 of worksheet number 2. Good luck, science fam.